Hello everyone, I am Deepak Paliwal. In the previous lecture, we have talked about the theoretical strength of the material, and we found that the theoretical strength of the material around 120 GPa if we consider some numbers. So the theoretical strength in the order of GPa, but actual strength in the practical scenario is only the MPa. So what is the reason of the strength reduction from GPa to the MPa? So what we have considered for the calculation that the material is defect free, but in the practical application the material is not defect free. It consists of various crystallographic defects. So what are the defects? Today we will discuss about the defects. The first, let us consider what kind of defects we have. So we are talking about the crystal defect. Okay, we have different types of defects. One is point defect. In the point defect we have vacancy, self interstitial, substitutional atom, Schottky defect, Frankel defect, okay, and etc. Another defect we have in the one dimensional point defect is also called as 0D defect. So we have, this is 0D defect. We have 1D defect, that is called as line defect. In line defect we have edge dislocation, screw dislocation. Then we have 2D defect. In 2D defect we have surface defects, or planar defect. In which we have our grain boundary, stacking faults, twin boundaries, tilt boundaries, etc. Again, we have volume defects, that is 3D defect, volume defects. In the volume defects we have inclusions, void, precipitates, and etc. So we have that many 0D, 1D, 2D, and 3D crystallographic defects, and because of all these defects, the strength of our material, which should be in the GPa, but we have strength in the order of MPa. So these all defects contribute to the reduction in the strength value. That's why we are getting the strength in the order of MPa. So we will discuss extensively line defects, various dislocation, whether edge dislocation or screw dislocation. But for the sake of introduction, we will try to understand the various 0D, 1D, 2D, and 3D defect in very brief. So first consider the point defects, which is the 0D defect. The first one is the vacancy. As the name suggests, suppose we have atoms inside the material. Okay, this is our material, and we have atoms. Suppose by some means these atoms go out, okay, or these atoms is going anywhere inside the material. So at this place, what we will have, like at this place, at this place we have vacancy. Okay, so this is the defect inside the material, we have atom missing. Okay, so this is the vacancy. Now from this concept only we can understand, suppose this atom displays, or this atom moves to here only. So this atom is called as the self interstitial. Why self interstitial? Because this atom is coming from the system only, or from this particular material only, and it is seated in the interstitial position. Interstitial positions are those positions which are made by the uh, neighboring atoms, or the existing atoms within the material. So that's why we are calling it uh, that's why we are calling it self interstitial. Okay, now if we talk about the substitutional case. Okay, again I am taking the example. This is our material, which consists of the number of atoms. We have vacancy here, and suppose the addition of atoms, like what we do alloying. So in that case, what we have, formation of solid solution. So suppose we did alloying, so the our atom gets placed here. So this atom size can be more than the blue color atom, or less than the blue color atom. Depending on the size, there will be a different stress field, whether it is tensile or compressive. Suppose we have 8 atom of its size more than the actual atom size. What it will do, it will give uh, it will give uh, compression in the neighboring atoms. So it will induce the compressive stress field. Suppose the size of the atom is smaller than original atom, then tensile stress field will be developed. Okay, so depending on the size of the atom, various stress field will be generated. So substitutional atom, and there is with the word substitutional, the important terminology will come substitutional solid solution. When the atom occupy the original lattice site. Suppose this atom is present over the original lattice site. So if the atom occupies the lattice site position, then it is called the substitutional solid solution. When the atom occupy any interstitial position, then it is called the interstitial solid solution. Okay, so we have substitutional and interstitial solid solution. So this is the discussion about the point defect. Now we will discuss about the surface defects. We will study the line defects in very detail, because our whole discussion of this course is related to the dislocation only, how the deformation of a material is taking place, and for the deformation, the dislocation plays a very much important role. So we will discuss the line defects in great detail. Before that, come to the 2D, when we talk about the grain boundary and twin boundary stacking faults. Okay, so we are talking about the 2D defects. First one is grain boundary. So first, what is the grain boundary? In case of the polycrystal material, suppose this is the polycrystal material. Okay, polycrystal material. So the one, suppose this is the first grain, this is the second grain. So first grain and the second grain, by saying the first grain and the second grain, this grain has the different orientation, and second grain has different orientation. Due to the difference in orientation, there will be a generation of boundary between these two grains. So the boundary which separate the two grains, that are called the grain boundaries. So these are the defects, because the periodicity is not maintained in this region, so whenever suppose any dislocation has to travel from this position to this position, it has to change the orientation from this grain orientation to the this grain orientation, then only this translation or this movement of this dislocation is possible. So this is a kind of defect. So what we can say, the boundary between the grain which has the two different orientation is known as the grain boundary, and the twin boundary is very much different. Suppose we have atoms, uh, suppose the like we have material, and we have applied the shear stress along this direction, suppose, and material is deformed like that. This is the your various unit cells, and we have deformed the material such that it forms like that. Okay, so the one part of the material become mirror image of the deformed part or other part. Suppose deformation is happening like that. Okay, so this plane 1, this is the plane 2, so the 1 becomes the mirror image of 2. Okay, so the boundary between the uh, twin regions is known as twin boundary. Again, now, after after having a brief discussion of the 2D defects, now we will discuss about the 3D defects. Okay, so the 3D defect again, how we can say 3D defect, which has voids, inclusions, and your precipitates. So how the precipitates are forming, suppose I am just taking the example of aluminum copper system, which is very well known system, and I am just making a very uh, this is temperature versus composition plot. Okay, temperature versus composition plot, and I am just plotting an extract of that phase diagram. So what is how the precipitates are forming inside the system. So in this particular system, aluminum copper system, we are talking about the mixing of copper inside aluminum. So we are talking about mixing of copper inside aluminum. So what would happen, like as we increase the temperature, solid solubility of copper in aluminum increases. Okay, now now if we quench quench the material, so the copper atom do not get sufficient time so that it can come out, like if we draw here. So what we did, we have heated the material in the single phase region and we suddenly quench it. So here the stable state is not a solid solution state. Okay, but we have done quenching, so the quenching does not allow time for atom to come out from this from the aluminum matrix. So when we did aging, or when we do aging, what will happen, the copper will get sufficient time, it will come out and form precipitates. So these precipitates, obviously these precipitates are contributing in the increasing the strength of the material, but it is termed as a crystallographic defect within the material. Apart from the defect, for the solid solution strengthening, or I am just giving extra information, solid solution. So what are the rules? Homer Audrey have given some rules to form a extensive solid solubility. And the very first rule that says the crystal structure of the elements we are mixing should be same. Crystal structure should be same. Okay, like copper aluminum, both are FCC material. Copper nickel, again FCC material, FCC crystal structure. Second thing, the size difference, like atomic radii difference should be less than 15%. Okay, third one is the vacancy, not vacancy, sorry, valency. So lower valency atom or element, not atom, element dissolve more amount of element with large valency or higher valency. Means element A suppose have valency 2, element B have 3, then what would happen, A can dissolve more B, but B dissolve A less. So these are the rules. These are not these rules are not mandatory, but these rules are important to form extensive solid solubility or higher solid solubility. Okay, so before going to the actual discussion of dislocation, we need to understand some terminology, like first is Berger vector, second one is line vector. First consider the Berger vector. Berger vector is denoted as B, and we know the vector has magnitude and direction both. So the Berger vector represents the shortest lattice translation. When we say shortest lattice translation, that means suppose we have abscissa unit cell. We know from the very first lecture that the atoms in the abscissa unit cell at the corner and at the face of the material, at the face of the unit cell. Okay, and the closest peg direction is closest peg direction in abscissa is, we know what is the closest peg direction is 110. Okay, so Berger vector, which represents shortest lattice translation. When I say lattice translation, that means when we move one atom to the another position, from one position to another position, our symmetry remains same, or our translation symmetry, all the symmetries remains preserved, then only we can call it lattice translation. Otherwise, if symmetries gets disturbed, then that would not be the lattice translation. So in case of the FCC, what would be our lattice translation? Our lattice translation, when we move our atom 1 to the 2 position, that means from corner atom, if we move from corner atom to the face centered position, means 110 half, then our translation is lattice translation, and all the symmetries of the FCC unit cells remains conserved. So then we can call it our Berger vector, and this Berger vector for FCC. Now for BCC, let me draw a unit cell, and we know where are our atoms in case of BCC. We have atom at the corners, and again we have atom at the body centered position, and 111 is the closed pegged direction. Again, the lattice translation, which represents the movement of atom such that all the symmetries remains conserved, then only we can call it the lattice translation, and this lattice translation represented by Berger vector. In case of BCC, that is 1 by 2. In case of BCC, it is 1 by 2, 111. In case of FCC, it is 1 by 2, 110. Okay. For the line direction, line direction represents vector along the line of dislocation, and it is represented by u prime a unit vector or line unit vector, which shows the direction of dislocation line. So in this lecture we have learned various crystal defect. First we have understand what is the reason behind the theoretical strength in order of GPA, but the practical strength in the order of MPa. So the main reason is that material consists of various defects: 0D defect, point defect, that means the vacancy, self-interstitial, substitutional atom, short key, Frankel. 1D defect means line defects, edge dislocation, screw dislocation. 2D defects, surface defects or planar defects like grain boundaries, stacking folds, twin boundaries, tilt boundaries. Okay, and 3D defect, volume defect, inclusions, voids, precipitates, etc. Then we have discussed in brief the various defects. Then we come to the Berger vector and line vector, which are important to define the dislocations or to understand the various dislocations. The Berger vector, which represents the shortest lattice translation. Lattice translation represents the movement of atoms in a unit cell, movement of what, translation of atoms from one position to another position, so that all the symmetries of with all the symmetries of this crystal structure remains preserved. So in case of FCC, we got 1 by 2 110. In case of BCC, we got 1 by 2 111. Then we uh, have taken the definition of line direction. So line direction, as simply name suggests, that it shows the vector along the line of dislocation. So that's it for the today, and thanks for the watching, and please do like and subscribe. And if you are liking any of these things, please do comment and mention, and what are the improvements needed for these video lectures. Your suggestions are welcome. So please support us, and please contribute in the improvement of this lecture series. Thank you.